Syzygy, episode 57, Ancient Stardust and Gaia Sausage. And welcome back for another edition of the Syzygy podcast. My name's Chris Stewart. Sitting opposite me at the table here, as ever, Emily Brunsden. Hi, Emily.
Hello, hello.
So today we're going to be talking about a rock that was found in the middle of nowhere in Australia. Apologies to anyone from the small town of Murchison. You're not necessarily right in the middle of nowhere, but, you know, very small place in Australia. A rock which was from outer space, and a meteorite which landed in Australia. And we're talking some time ago now. And that's not news. What is news is what was inside it, which was a little bit of what's been making the news rounds lately as stardust. Ancient stardust. Older than pretty much everything else around us. So we're going to be talking a little bit about stardust and meteorites today. But Emily, we've got a little bit of follow-up that we need to do. Last time we talked about the big red star Betelgeuse up there in Orion's armpit, if I'm not mistaken. Yep. Betelgeuse, has it exploded yet?
No.
No, okay. So cross that one off. That's not follow-up. But we found something else in the vicinity that clearly has, or something interesting's happened.
Yeah, another thing hit the headlines not long after we recorded the episode, which was that we found some gravitational waves in the direction of Betelgeuse.
Now, gravitational waves, we can only see those when something really big has happened, so Betelgeuse has exploded.
Not quite.
No? Oh,
no.
That's disappointing.
So, I mean, this is just one of those things that it just so happened that we got a very small detection of gravitational waves in a bit of the sky that's roughly in the same kind of direction as Betelgeuse. Now, this is such a non-news story because as soon as you go and read the articles, they say, well, you know, it happened in this direction. But the actual localization which you get from the gravitational wave detectors is not near Betelgeuse, first of all.
Right.
It's a bit, it's off to the side.
In the same general vague vicinity of the sky as Betelgeuse, but
not the same localization, not unfortunately. The gravitational wave signal is probably too short to have been from a supernova, so we'd expect something a bit longer. Actually, maybe this isn't even a real gravitational wave signature. So there's a lot of testing. There's a lot of false alarms that come through. I mean, we're right on the edge of our capacity to detect gravitational waves, right? This is the cutting edge. And so you do get signals that creep in from time to time that aren't really real. Mm-hmm. And so
this could be one of those.
Event hasn't actually gone through all its false alarm checks yet.
Yeah. I mean, remember when you're talking about detecting gravitational waves, you're talking about, you know, these very long lasers heading off across the desert down at LIGO in orthogonal directions, 90-degree directions. And you're talking about a difference in path length for those lasers when a gravitational wave comes through and wobbles everything around. It changes the distance by a tiny fraction of the diameter of an atom. Like, these are really, really, really ludicrously small, fine-grained measurements. And so, you'd expect to get a couple of false signals coming through.
Indeed, yeah. So all those checks and balances haven't been done yet. So it may well not even be a real signal at all.
Sure.
And even if all those things weren't true, then we haven't detected any increase in the neutrino signal that we're getting from space.
And you'd get a lot of neutrinos
and just
from
like gravitational
a big
waves,
honking explosion.
Yeah, neutrinos and gravitational waves are the first thing we'd see from a supernova. So without one...
So pretty clearly this is not Betelgeuse or indeed any other star exploding No. Just really bad timing then, given that the world sort of went into, hey, Betelgeuse is about to explode, and then, hey, look, we found these gravitational waves. Oh, great, Betelgeuse has exploded. No, it hasn't.
Yeah. So well
everyone.
Done, media, for all those non-stories.
Remember episode 56, last week's episode of this podcast. We've got roughly a time frame of about 100,000 years over which Betelgeuse might explode. Indeed. So just everyone kick back and relax. Get some popcorn. If you want to watch it, it's going to take a while. Okay? Don't get too excited. So that's enough of that. We can move on, I think, from Betelgeuse on to the topic du jour, which is stardust inside meteorites in outback Australia. Emily, what's going on?
Well, this is so exciting because we've now found the oldest known material on Earth, and it's older than the meteorite. It's older than the Earth. It's older than the sun. In fact, it's older than our entire solar system.
Okay, now that just doesn't sound right on so many entire whole levels of older thans here. How can you, I'm just going to ask the obvious question, how can you have something inside a meteorite which is older than the meteorite, which is older than the planet that the meteorite is sitting on, which is older than the star that the planet is orbiting that the meteorite is sitting on, which is older than the entire solar system within which the star and the planet and the meteorite exist? That sounds to me like a logical paradox that is impossible to solve. So I'm guessing that for the next half an hour or so, we're going to have a little bit of a chat about that just unpick this one to find out where that logical fallacy falls apart. What are we talking about?
Yeah. So, well, let's have a think about what might have been around before the sun. So,
okay, let's go right back.
The sun is just a twinkle in the galaxy's eye, if you like.
Right, okay. It's actually fairly young, isn't it?
It is fairly young.
Yeah,
so the sun's
for a
around
star.
5 billion years old.
Which is young for a star, apparently.
Well, middle-aged.
Yeah,
maybe.
middle-aged, okay.
Yeah, let's say. So the whole galaxy is older than that. We're not greatly sure on how exactly old, but some of our measurements of the galaxy suggest it formed pretty early on in the universe. The whole universe is something like 13.7 billion years old.
Right. And so 5 billion, okay, that's been around for a while, but there are things which are much older than that.
Yeah. So the whole galaxy is definitely older than that. And what we are thinking about is, okay, before the sun appeared, there was stuff in the galaxy. There were grains of dust, for example.
Well, I mean, the sun had to come from somewhere.
Exactly. So there was lots of gas and dust. And these grains of material were formed in previous generations of stars. So stars have a cyclic life cycle, if you like, and they go through their birth, they evolve and they die. And some stars do that faster than others, but it means that every successive generation of stars is made up of all the stuff that the previous generation spat out back into the interstellar medium beforehand.
Right. So much earlier in the universe, much earlier in the galaxy, you would have had stars which lived through their life cycle, exploded or ended in the way that they end, and spat stuff out into the cosmos, which then would have coalesced again into the next generation. How many generations through would we be then? What generation would the sun be?
That's interesting. We tend to talk about populations of stars rather than generations because we don't know exactly. And of course, the sun's made up of lots of different bits, and bits of those could have gone through one generation of stars, and some of it could have gone through 17.
Sure.
It's sort of, so we have populations of stars which we base on how many of these higher metals or elements that are higher than hydrogen and helium, because every successive life cycle of a star puts more higher elements back into the system. So if you form with a lot of high elements, lots of iron, lots of magnesium, things like that, then you must have been born later than a star that's just pure hydrogen and helium.
Right. That makes sense, because in the very early universe, there was really only just hydrogen and helium, wasn't there?
Yeah.
That's all there was. There weren't any of the larger elements, or scant amounts of them, very, very small amounts. But those larger, heavier elements get made in the cores of stars, or get made when stars explode.
Yeah.
Don't they? And
exactly.
so it's only they're only going to be around if you're several generations down.
So the stars like our sun, which have fairly abundant species of these metals, we call them population 1 stars. So lots of things are like that in the local universe around us. We have also population 2 stars, which are old stars. And these tend to be stars that were born maybe 7-8 billion years ago. So they've got fewer metals. Globular clusters are a great place to go look for those types of stars. And we have a third classification, which is still hypothetical, which is called population 3 stars. And we hypothesize that these were the very first kind of stars that were born in our galaxy.
Now, why are they hypothetical? We can't see them. We can't tell. We don't know to look at a star whether or not.
We haven't seen any.
Right.
But we don't really expect to see very many at all, because most of those stars will have completed their life cycle. It turns out the more mass you have, the faster you progress through your life as a star.
Right. More mass, which means more gravitational attraction. Everything's squashed together more, which means you run through the nuclear cycle faster, the fusion cycles.
Exactly.
And you burn out, and eventually you die.
Yep.
Okay.
So there's a couple of compounding factors. So you've got the fact that these population 3 stars were the very high mass ones were gone very, very quickly. They only last a couple of million years. But even stars that are kind of the mass of the sun are coming towards the end of their lifetimes now. So it's quite hard to pick out these the lower mass stars. We do think that the stars, the very low mass ones, are still around, but there are compounding factors that think, well, if you're only made of hydrogen and helium, that changes a little bit the speed at which you move through your life. It probably speeds up. And there was probably a preference for very, very high mass stars in the early galaxy as well. So there were probably fewer of these low mass.
Right, so it's a bit of a selective process. You wouldn't expect at this point to find terribly many of these hypothetical, what did you call them?
Population
3 stars. Yeah. Cool, okay.
But maybe we can one day.
Yeah, we'll see. All right, so that gives us a little bit of background on where our sun and our solar system sort of sits within the history of stuff in the universe. Okay, so where do we go from there?
So the previous generations of stars were putting things back into what we call interstellar medium. That's the space between stars. And the interstellar medium is not empty. And especially in the galaxy. I mean, you think about the lovely pictures you see of galaxies. They've got these beautiful spiral arms. Those are not just made up of stars. That you can see the gas and glowing.
Gas and dust and stuff.
Yeah.
Galaxy stuff.
So it's mostly gas. About 1% of that interstellar medium, however, is dust.
Right.
And we call this cosmic dust. Or even more specifically, pre-solar grains, because these are pre-solar system. So they're grains of stuff.
And you're talking about, you put it like grains and dust, like you're literally talking about tiny little
solid
bits
things.
of, like we would think of dust as like anything from, skin particles through to basically, very small grains of sand, rock, stuff, little grains of material. That's literally what you're talking about when you're talking about dust in the galaxy.
Yeah, so it's not skin.
Well,
it's
that
not
we
the
know
same,
of. No,
it's not the same dust that you find under your bed.
No,
but it is, and it's actually a lot smaller than what you might think of as dust as well. So it's about the size of cigarette smoke.
Okay,
so it's about
it's little
micron
particles
size.
of stuff.
Yeah, tiny little particles.
As opposed to atoms and molecules, it's bigger than that.
It's bigger than
chunks.
that. Yeah, so it's things like silicates. So compounds, and often. These are solids in the interstellar medium, so that's why they're these small particles. Mm-hmm. And so about 1% of the entire mass of the interstellar medium is made up of this dust, which is not huge, but it's enough that means when you form a star, those compounds go into the star. And indeed, if you have bits that are left around, kicking around your solar system after you've formed your star, and the disk that formed around the protostar is now forming rocks and planets and things like that, some of those can get trapped in those objects as well. Which
brings us to our meteorite found in Murchison in Australia. So what has been found exactly?
Yeah, this is a great meteorite. I love it. This is one of the world's...
This is a really famous one, isn't it?
It's a very, very famous one. It's probably one of the most famous meteorites. It's called the Murchison Meteorite.
All right, tell us about the Murchison Meteorite.
Well, so it's a great story that goes with it as well, because it's one of the few that we've actually seen fall, and we've been able to collect up the stuff that's been impacted into the Earth.
Because, meteorites come through a lot. Meteorites are the ones that reach the ground, aren't they? So meteors don't necessarily reach the ground, but meteorites are the lumps of rock that actually do. And you see shooting stars all the time, like stuff is hitting the atmosphere all the time. Presumably, small amounts of stuff are hitting the ground fairly regularly, but actually seeing one and then going and finding it doesn't happen very often.
No, it's quite rare. And most of the meteorites we've sort of collected up, but they could have fallen to the Earth thousands, millions of years ago. So having one that you see and it's fallen to the ground gives you a real opportunity, because you can go and instantly kind of preserve it, and it's pristine, and it's exactly what you think it is.
Go and find that smoking lump of rock in the crater and scoop it up and take it away.
Yeah. So the Murchison one fell in 1969.
Okay.
And it was observed by lots of people because, Murchison is not super, I guess it's quite small, but when you're just
it's not right out there. Like, Australia's got a lot of open space that you wouldn't go and find a meteorite in because there's no one there. But this one was close enough to enough people that it could be seen and found.
Yeah. And it was a giant fireball in the sky and made a lot of noise, so you tend to notice when that happens.
What was that? Quick, over here, everyone. There's a big smoking crater. Yeah, okay.
Yeah, so in this case, there wasn't a big smoking crater. So the whole meteorite that fell, kind of exploded as it was in the atmosphere, which often happens with meteorites. You might have even seen footage of the Russian meteorite, for example, that did the same thing.
When was that? A couple of years ago?
Probably more than a couple.
Yeah, a couple of years ago. Well... Okay, I remember seeing some footage over the last several years, and maybe there's been a few cases of bloody great fireballs going across the sky, and it typically is in Russia. And I don't know if that's because almost all Russians now seem to drive around with cameras on their dashboards now, looking out the front.
It's quite helpful.
Very helpful for not just spotting car accidents, but also spotting meteors. Who knew? Anyway, yes.
Yeah, so they often disintegrate in the atmosphere because these things are getting superheated. And if there's any kind of gas or liquids, water, for example, that becomes superheated, it can expand very quickly, crack the whole meteorite open and sort of disintegrate the whole thing. So that happens relatively often. It's especially for these smaller, let's say, in inverted commas, meteorites. If you're going to think about an enormous thing that, for example, the size of the object which wiped out the dinosaurs, that has more chance of staying together because the interior stays colder.
Yeah, and that actually hits the ground and makes it bloody enormous. But I do remember the one which was 100 or something years ago. I mean, I don't remember it personally. I wasn't there. I'm not quite that old. But the Tunguska blast of, I don't know. I mean, it's famous for being mentioned in Ghostbusters is all I remember. But that was amazing because it did explode. It didn't hit the ground as far as we know. But it wiped out, like knocked down all the trees and burnt them to the ground for, I don't know what the radius was, but it was miles. It was huge. We'll put some pictures and links in the show notes. But that was amazing. And it was a huge explosion of a meteor in the atmosphere.
So enormous amounts of energy.
Yep.
It's really what's happening with these things. So this one, it's sort of the fireball in the sky. It fragmented. There was a tremor that was felt in Murchison by the local observers. And that was really helpful because we could see that, okay, this meteorite's fallen. It fell into so many different pieces. In fact, the largest piece they found was only about 7 kilos.
Okay, so that's a chunk of rock, but it's not an enormous chunk of rock.
No, but collecting up all the little bits that they found across the entire area, they managed to put together about 100 kilos of meteorite.
Wow, that's impressive. Okay, so we got quite a few pieces of the Murchison meteorite.
Yep.
But why is it? I mean, I guess it's famous because we saw it and then we found it and we managed to get all these pieces. But what is it? What's it useful for? What has it told us?
Well, it's one of these ones because you saw it and you collected it quite quickly. You're able to preserve it and keep it in as pristine condition as possible. So it's been one of the most experimented on meteorites.
Right. So it hasn't been sitting there weathering away in the desert and getting contaminated by the local surroundings. This is, as you say, pretty much straight out of space.
Yeah.
Cool.
Really nice. So it's a really interesting type of meteorite too. It's one of the rarer types. It's called, I'm going to try and get this one right.
Give it a go.
I'm not a great chemist.
Come on, give it a go.
It's a carbonaceous conondrite.
Give that another?
Carbonaceous conondrite.
Okay, sounds legit.
What that means is that it's really carbon rich.
Okay.
And these are the meteorites that we've found in the past do contain stardust, and it's less than 5% of all meteorites that do contain kind of some stellar and pre-stellar grains, shall we say. So really carbon rich, really primitive materials. It's one of the things I found out about these meteorites, which is really quite cool, is that you can find lots of organics in them, organic compounds. And
now, organic, despite the name, we always need to be a little bit careful about this. Organic chemistry doesn't mean life. It's a particular set of or group of chemical compounds, chemical reactions that we talk about in organic chemistry, which do occur in biological things, but it doesn't mean organic chemistry happens in all sorts of places where there isn't life, as well as all sorts of places where there is life. So let's just be careful on that. We're not saying that there are aliens inside this meteorite.
No, but what's really interesting is we see the same organic compounds that we see when we try to make life from scratch. Now, I'm going to be careful here because there's a really famous experiment which is called the Miller-Urey experiment, and what they did was they took what they imagined were going to be the primordial conditions of Earth and tried to sort of make life in the lab. That sounds very...
It sounds like you really do need sort of a...
Frankenstein kind of,
kind of laugh.
But no, what they were doing was they took how they imagined the atmosphere to be and what the oceans were like.
The primordial soup.
Exactly.
Yes.
What were the preconditions? And then they added energy into the system via an electric kind of charge.
Tell me they used lightning and one of those big ka-chunk type switches.
Maybe.
I really, you would, wouldn't you? You'd put that in the grant application.
We think that lightning is the precursor, but yeah. And then they just recycled this again and again and again and again and again. And then after, I think it was only a couple of weeks, they managed to recreate these very primitive organic compounds.
Mm-hmm.
And so it's these same organic compounds that we see in meteorites. So there's kind of a link there to early precursors of life. That's not to say that's a living thing.
No.
But it's some of the building blocks.
Yeah. You're sort of putting the things in place that maybe go on to produce this. Anyway, so that's cool. You find organics.
Yeah, and there's there's iron in these. So you've got about 22% iron and 12% water in these meteorites. So these are the ones that you find these pre-solar grains. Now, these are tiny little bits. In this paper that the researchers come from, which is a paper by Hackenal, who come from Chicago, he has quite a lot of associations with various different organizations, shall we say, so different planetary sciences, universities, and things like that.
He's from everywhere.
Yeah. So what they've done is they've kind of split this bit of this meteorite open, and so that's pristine inside because that wasn't touched by any process on Earth.
Right. Yeah, it's not the surface. You're getting right down into the middle.
Yep. And they found 40 of these grains, and the grains are of a species of silicon carbide. And they were able to then take these grains and date them and say, well, how old are these grains?
Okay.
And it's not an easy process, actually, figuring out
how do you determine the age of a tiny little chunk of silicon carbide? I mean, you can't ask it. It's not written on it. What do? You can't.
Well, it's interesting because we do have ways of dating materials. You've probably heard of things like carbon dating.
Right.
So carbon dating, we look at the different isotopes of carbon and we look at the radioactive decay, and we know how fast radioactive decay happens, so we can say how long that particular bit of carbon, if you like, has been around for.
Sure. I guess you work it backwards and you say when this thing was formed or made or buried underground or whatever it might have been, then if we assume that there are the same ratios of radioactive to not radioactive carbon around then as there are now, then you look at the ratios in this object that are around now and you can figure out, well, there's much less radioactive carbon than there would be if this thing was sort of made now. Therefore, it must be this old. That radioactive carbon has decayed, it's gone away, and you can work backwards and go, therefore, it's 20,000 years old or whatever it might be, because you know how quickly the carbon decays, the radioactive carbon decays. So you're doing something similar for grains of Stardust?
Not exactly. You can't use those because there's lots of things that decay radioactively. It doesn't have to be just carbon. But you can't use those processes as well for things that are from, say, pre-solar system because you don't really know the 0 point. You don't know how much of a radioactive isotope of any substance there was when you formed your particular solar grain.
Yeah, carbon dating on Earth makes the assumption that things, tens, hundreds of thousands of years ago were roughly as they are now in terms of ratios of isotopes.
Yeah. If you look at a tree now and you look at a tree from, thousands of years ago, it probably had a similar carbon ratio. Right? Yeah. Whereas if you've got a dust grain, it's kind of like, well, we have no idea where this was formed in the galaxy, what kind of things have been exposed to it. So it's really hard to do those.
So we don't have that zero baseline, so we can't compare it against anything to say, therefore it is this many billion years old. So what do you do?
Well, we do a similar thing, but it's kind of taken from a different angle. So instead we'd say, well, how long has this particular dust grain been exposed to high energy cosmic rays?
Ah, okay. Cosmic rays out in space, which are coming from... Now, remind me, when we talk about cosmic rays, where are they from? What are they from?
Super high energy, they come from supernova, they come from very energetic stars, lots of black hole processes. So these things are sort of swizzing around. They come... most of them are protected from hitting the Earth, from the Earth's atmosphere or various processes.
But the point is they're flinging around through space, very high energy... particles or photons from very high energy processes spread throughout the galaxy, throughout the universe, coming from all over the place. And that's a fairly constant background?
Well, at least constant enough that we can do some modelling with them.
Okay.
So if we say, well, how long was this object exposed to cosmic rays? Now, cosmic rays will penetrate into, for example, these grains, and they will cause different nuclear reactions. So what they're particularly looking at is a neon, and it's neon-21 isotope. And you can look at how much of this neon-21 isotope has been produced.
Wow, that's pretty specific.
Yes. Well, they did test a lot of other isotopes.
Yeah.
I didn't read all of their testing. It was
You didn't go
very
that deep.
extensive.
Yeah.
And they did a great job.
But the point is,
neon was the best one.
a little bit like the carbon dating. You use carbon for carbon dating because it's got a really useful property that, we understand a lot about it. We know that there's plenty of it on Earth, and we know what it does. You've got to go looking for something similar if you're going to date things in other ways. And there are a bunch of other possible reactions that could have gone on, but presumably the neon is the one they've lent on to say, this one works, this one's good.
Yeah. So that was the best one that came out of the research. So they were able to look at the quantity of this neon-21 isotope in those grains, and therefore date will at least say how long they were out there in the in stellar medium before they kind of got captured into this meteorite. So we got some results.
Excellent.
Most of the grains were between about 4.6 and 4.9 billion years old.
Okay. Now, a little while ago, you told me that the sun is about 5 billion?
It's about 5, so I've kind of rounded up a bit there.
Okay,
maybe 4.6 to 5.
Okay, sure.
So
in the order of the age of the sun.
Yeah.
Okay.
So they're similar age to the sun. But there were a few grains that were found to be much older than this. And they were dated between 5 and the oldest was about 7 billion years.
So that's quite a lot older. So hence the name pre-solar. Grains. Right. So these things have been around floating out there in the interstellar medium for longer than we have. We collectively being the entire solar system.
Exactly, yeah.
Which is very cool.
So we think that these got captured into the meteorite during the formation kind of era of the solar system. So probably, again, around 4.6 billion years ago. And they've just sat there kind of ever since. But they've been
waiting
kind of preserved.
to be discovered.
Yeah, by this meteorite.
And so they would have been captured. I mean, we've talked about this before on the podcast, that you start off with just a big cloud of dust and gas and stuff, which slowly but surely coalesces under a couple of different processes. One is sort of gravitational, things clump together. But the other is also that I think you used the phrase before that these things are sort of a bit sticky, whether that's electrostatically sticky or chemically sticky. And you get tiny grains, which then clump together to make slightly bigger grains, which then clump together to make bigger grains. And slowly but surely you build up chunks of stuff, which can be meteors or they can be planets, moons, even bigger things. But this is all that's happened here, is that you've got grains which are very old, which slowly but surely just clump together. And eventually you get a meteorite which has got these little things inside it, landing in the middle of Australia.
Yeah, so a small fraction, probably less than a percent of all the dust in our solar system that then went on to make all this stuff was composed of these pre-solar grains. So they will actually be found in the Earth. They will be found in the Moon. They've made their way into all these objects, but the hard thing is that all these other geological processes, including sort of lots of nuclear reactions, happen inside the Earth. You've got lots of decay. You've got cosmic rays coming from space. So you're really, really stuck trying to actually find those objects from geologically active planets.
We assume that they're there, but we'd have Buckley's chance of actually nailing any of them down here on Earth and saying, oh, that bit there, that's clearly pre-solar grain because it's been influenced by the fact that it's actually on the planet for 5 billion years. I mean, is the Earth, do we sort of take the Earth's age as roughly the same age?
Yeah,
as
about 4.5, something like that. Yeah.
Okay. So that really messes up everything. Whereas if you've got one that's sitting in the middle of a meteorite, then that's a much easier thing to nail down.
Exactly, yeah. So it's really, really interesting stuff. And so there's been a few kind of really good discoveries. I mean, there's only 40 grains, which sounds small, but it's enough to make some statistical projections.
Sure. I mean, that's a very tiny amount of sand in your palm, but that's better than one. So what have they found?
So, as I say, most of these grains were found between 4.6 and 4.9 billion years old. In fact, almost too many. If you sort of expected a random kind of mixture of pre-solar material, you should get some which comes from a star over there and some which came from a star over there. And they should have been ejected and put into the interstellar medium at quite different times.
Sure.
But in fact, there's kind of an overabundance of these grains that are dated in a very similar region.
Okay. So what do they think's going on there?
So it suggests that maybe there was an increased or an elevated period of star formation in our galaxy, something like 7 billion years ago.
Right. Okay.
So if you think that ties in with the 4.5 to 4.9, because if you think a star is born 7 billion years ago, it's going to take a few billion years to go through its life and then die and then eject this material back into the interstellar medium.
Yeah, as you say, the really big ones are going through it in sort of tens of millions, but smaller ones, hundreds of millions, billions of years, you're still going through quite a few stars if there was a lot of star formation 7 billion years ago.
Yeah.
Yeah, okay.
So it seems to be that there was this kind of increased rate of forming stars in our galaxy. And now here's where this gets quite cool. And I'm not sure how well developed this link is, but
Sure.
I like it. It sounds nice.
Let's go with it anyway.
If we're going to explain why there were more stars formed about 7 billion years ago, we've got one clue.
Mm-hmm.
And it comes from Gaia, which is a ESA space telescope. And Gaia's mission is called galactic archaeology. So that interesting.
Which is a very cool
It's
term.
a very cool
Throw
term.
that one around at a party. What do you do? Well, I'm a galactic archaeologist. You'll be having free drinks all night.
It's fascinating stuff. So Gaia is mapping more than 1 billion stars in our galaxy, and it's very, very precisely mapping things like distances, brightness, etc. But it's also really interested in overall sort of compositions of objects. So we can start to say really global things about independent structures in our galaxy, and it's fascinating, all the stuff that's coming out of Gaia. So that one of these things which came out was something called the Gaia sausage.
The Gaia sausage.
The Gaia sausage.
All right, go on
Love
then.
this.
I'm keen.
So the Gaia sausage was named because when they plotted some of the stars, or there were a huge number of the stars, you make these enormous plots with thousands and millions of stars in a single plot. But there was a particular plot whereby it looked like you had kind of the normal disk of the Milky Way, and then just below it there was this giant structure that shouldn't really be there, that was just a big sausage.
So hang on, just to back up us again, you're talking about measuring where stars are in the galaxy and sort of, exactly where in 3D space these things are, how far apart they are and so on. And there's a sausage.
It's not a geometric sausage. It's not actually a thing you can go and see in the sky.
Okay.
It's just if you plot the Gaia data in a particular way.
Right.
Out
You'd
falls a
expect it.
sausage.
You'd expect it to be sort of over here, and then, well, what's this sausage-shaped thing on the graph over here?
Yeah.
It's the Gaia sausage. And what does the Gaia sausage tell us?
The Gaia sausage actually also points to a period of increased star formation in our galaxy. And it's to do with the fact that we had a merger with another galaxy. So there was a Gaia Enceladus merger event, and this was a galaxy that was much, much bigger than most of the dwarf galaxies that we are currently merging with today. But somewhere around about 8 to 11 billion years ago, there was this fairly large galaxy that merged with the Milky Way. And so the Gaia sausage is actually the leftover bits of that merger, if you like.
Right.
So the sausage bit are the bits, the stars that used to be in the other galaxy. And it's incredible because it seems that we got at least 8 globular clusters, so big old clusters of stars, and maybe something like 50 billion solar masses worth of stars from this other galaxy.
Wow, that's a lot.
It's a lot.
That's a lot.
Well, we're only something like 300 billion stars in total.
Yeah.
So, yeah, we poached
So
quite a lot of stars.
adding in another 50 billion solar masses worth that's quite a lot.
Yeah.
Okay.
So lots of stars.
And this
got
is
added
all
in.
kind of happening in the roughly 7 billion.
Yeah,
years
and
ago.
and roughly in this right period.
Wow.
And so what we see that the disk of the galaxy during this merger is kind of puffed up. It used to be kind of, the galactic disk was quite thin, but lots of gravitational interaction puffed up the disk, fluffed it up, and therefore it would make sense that there was a huge star formation event around about the same time.
Awesome. Which then would have led to lots of stars living and going through their thing and dying and spitting out grains into the interstellar medium, a few of which got mopped up by this particular bit of rock, which then flung itself down into the Australian desert, 50-something years ago.
Now, I have to say that those are a lot of dots that are kind of tenuously connected.
Yeah. I mean, I was about to say, that sounds like a really good story. How confident are we in this story?
Well, it's like you've got dot to dot, but in the sense that you know the dots,
Yeah.
you just don't know what the lines between them are. So
Sure.
it's one way you could draw a line between, say, an increased period of star formation and what the Gaia results are.
Sure. Okay.
But it may not be the only way.
It's a plausible explanation for what we found.
Yeah. So that's quite cool.
Nice.
The other major finding from this work is that actually these grains tend to be a lot stickier than we perhaps thought.
What do you mean?
So this actual size of the grains, the clumpiness of them, seems to be a bit bigger than you might expect for something that's kind of a few billion years old.
Okay.
And what that means is that these grains have survived in the interstellar medium through some pretty harsh conditions, right? For example, if there's supernova shock waves traveling through the interstellar medium, we would expect that they would break up these kinds of grains.
Yeah, I mean, a supernova shockwave is one hell of a shockwave. That's, that's not just a little thing. That's a big thing.
That's a big thing.
Yeah.
And so we would expect the actual grain size to be smaller.
Mm-hmm.
But indeed, these things seem to have stuck together and become clumpy objects and survived, which is interesting as well, because it means that when we do model how dust processes work in the galaxy and how they feed into star formation, we need to take account of that kind of clumpiness in our models as well.
So it's teaching us more about how these processes actually work and how the dust actually forms and sticks around.
Yeah.
Which helps us with understanding of galactic evolution, that kind of thing.
Exactly. Yeah. So again, galactic archaeology, looking at the evolution of our entire galaxy, and it is like archaeology in a sense. You're looking at a fossil record. You're looking at what we have left over from processes that happened billions of years ago.
Yeah, I hadn't really thought of that. I mean, archaeology is typically, as Eddie Izzard used to put it, you're digging up a desert and going, it's a series of small walls. There's always a series of, and what happened here? And you're interpreting from what looks to the untrained eye like it's just a pile of rubble, and you're interpreting, yes, but they would have been eating over here and over there. They clearly had the toilets. And from this, you're able to, we've got tiny little clumps of stuff, and so the rest of us is great. Okay, you've got sand, well done. But no, it's really interesting because the grains are bigger than we thought they would be. And no, that's really interesting. That tells us a lot about the galaxy. That's really cool.
It is really interesting. And the more, of course, that we learn about both star formation processes in our galaxy, even the whole evolution of our galaxy, it tells us more, therefore, about how other galaxies evolve. Physics is one of these wonderful things that when you work out how something works, you can apply it to a whole lot of different contexts.
Yeah. It's just one huge jigsaw puzzle. I love it.
Yeah. So if we come to sort of you're going to ask the next question.
Yeah. Which is
your favourite question.
And so what?
Yes. Excellent.
Yes.
I prepared for this question.
We've reached that part. I can tell by the look in your eyes, Emily. You have an answer.
Yeah, I
so
do
what?
have some
Let
answers.
me tell you something.
Well, as we've just been talking about, actually learning about the solar system is really interesting. Learning about conditions pre-solar system. I mean, with direct evidence, that's very cool. We often think about astronomy as this science where you get a telescope, you go look at stuff. You want to learn more, you build a bigger telescope, you go look at more distant things.
We
right?
need bigger telescopes, more money.
But even
Which is true.
It is true, but it's not the only truth.
Yeah.
Even looking at things like Betelgeuse, a very, very close by star, don't really need a big telescope to study Betelgeuse, at least unless you want to do interferometry. That's really hard.
Yeah.
But, there's lots of things we can study that are close by that we're still learning about. And isn't it wonderful that we can actually study the history of our galaxy pre the sun by just going out there and grabbing a few rocks off the ground.
Yeah, it's not
on
looking
Earth.
through telescopes at all.
No.
There's a chunk of the universe just over here. If we go and have a look at that and apply some chemistry to it and apply that then to what do we know, what do we assume about what's going on out there? Do those two things match up? What can it tell us? That is brilliant. That's astronomy of a completely different kind.
It is, and it feeds into all our other technological developments. I mean, because this Murchison Meteorite's been around for ages, right, 60s. But we can continually develop new techniques of finding out new things about it because our own technology here on Earth is developing. We didn't have scanning electron microscopes when this meteorite fell, right?
No.
We needed those to get the images that are in the beautiful images of these little grains. And so the constant development of technology on Earth is able to be applied to astronomy as well.
Yeah.
And I really like that.
It's that notion that, I mean, we've got so much data. I mean, data from telescopes, but also data from, or literal samples of stuff that's fallen from the sky. and our ability to analyze that data is forever improving. There's so much work to be done. You guys are never going to be out of a job.
Well, yeah, and I do have to confess that this kind of stuff was, when I was quite young, going to be my interest in astronomy. I thought, you know what, I'm quite interested in geology. I'm quite interested in astronomy. Let's just,
I want to be a meteorite hunter.
I want to go study space rocks on the moon kind of thing. Yeah.
Where's my Indiana Jones hat? Da, 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 da. You'll be that person going out and finding them in the desert and then discovering all sorts of things.
Yeah, and then I decided that actually geology involves quite a lot of effort and you have to go climb volcanoes and...
But surely that's the fun part, isn't it?
Well, maybe, but it also sounded like a lot of hard work and very harsh sunlight, so I decided maybe some nice telescope work in the nighttime.
Where can I go where I can do it in my pajamas?
Yeah. That's nice. And, there are some things that I look back and I think, that was a good decision. I mean, some of the wonderful things that I read in this article was when they were describing the process of how they got the results. How do they actually analyze this? Mm-hmm. And so they're talking about, crush up the meteorite, make it into some kind of paste. And at this point, one of the researchers described this crushed paste as having the smell of rotten peanut butter.
Nice. I like how they actually even had a word for that.
Rotten peanut butter.
What does that smell like to you? It's kind of peanut buttery, but like off.
Yeah. And at that point, I thought, well, actually, I'm quite glad you're doing that research. None of my research smells like rotten peanut butter, but well done for doing it.
Well, we're going to have to find our way out of this thing for the end of another episode. Emily, I love the idea that inside a chunk of rock in the middle of the Australian desert, you can find ancient stardust, older than the entire solar system. That blows my mind.
It's so cool. And, we've got a meteorite on the Astro campus, and when we pass it around, when people come to visit us, we sort of say, this is the oldest thing you're ever going to touch.
Where's that from?
So our one's from South America. Mm-hmm. We bought it on eBay.
Of course you did.
Because there's enough meteorites to go around. I get that our meteorite's not the right type necessarily to have pre-solar grains, but there's a non-zero chance that it could be. So, and
it makes a really good story.
It could well be that when next time you hold a meteorite, it might actually hold things that are older than the solar system itself.
That's just so cool. Oh, well, listen, we've got to get out of here. Emily, if people want to get in touch with us and talk to us about the time that they held a piece of ancient rock in their hand, or ask us a question, or just say hello, how do people find us?
So we are at SyzygyPod on Twitter.
We are, and indeed lots of social medias.
Indeed. Facebook, we're on Instagram, and we've got a beautiful, beautiful website, which is syzygy.fm.
That's right. So you can go and find us there. There's a contact form there that you can say hello on. A couple of people have done that over the last 18 months or so that we've been running the show, and sometimes we even turned it into an entire episode based on their question.
Yeah, well, a shout out to your mum, who I think suggested this week's episode.
Indeed, she did. I wasn't necessarily going to mention that. But listen, if you are out there and you are a relative, or even if you're not a relative of us and you want to get in touch, that's how you can do it.
Oh, you've got to give a good shout out for your mum.
I do. She's one of our longest
number one
fan listeners. Hey, Mum. Glad you're listening. That's lovely. Otherwise, what else have we got? You can support the show in a whole bunch of different ways. Give us a review. Give us some stars on your podcast player of choice. And that'll really help us to rise up through the noise. In case you hadn't noticed, there are quite a few podcasts out there. And so you talking us up and giving us a positive review really does help us to float up through the dross. You can also go to patreon.com/syzygypod to throw a few dollars our way to help us keep the lights on here at Syzygy HQ and continue improving what we do. Otherwise, we'll be back again in, a week or so's time for another bit of universal cosmic podcast goodness. Catch you later, Emily.
See you later.
See you in a week. Bye, everybody. Right. Excellent. We need a title. So what about...
Things that are older than Chris himself.
Oh, nice.
It's always a good joke when you have the adults and you say, this is the oldest thing you're ever going to touch. Don't look at your partner when you think about that.
It reminds me of, before my honours year, I went to ANU in Canberra to do one of their summer research program things. You know how universities bribe students to come down in the hope that they'll stay. And I remember going around the physics department and talking to various people. And it's like, I don't know what I want to do. What are you doing? And I spoke to two people, one of whom was string theorist, come and do string theory, despite the fact that you've actually barely done any quantum at this point. Come and do 2 months of string theory with me, which is what I ended up doing, which was stupid because I didn't understand anything.
Wow.
Like literally nothing. When I did my PhD and my supervisor saying, so tell me about this string theory stuff that you did. I can't. I literally can't tell you anything. But the other one that I spoke to was a guy who worked with the particle accelerator in Canberra. They have a very small particle accelerator, which they use to blast samples in order to study the materials that they're looking at. And his project was, okay, come and spend a summer with us, abseiling down cliff faces, taking samples out, and then taking them in and blasting them in the particle accelerator. And for some stupid reason, I said no. I want to go and talk to this guy over here who's a nerdy theorist about stuff that I don't understand.
It's the pajama thing again, I think, Chris.
I think it is. And I kind of to this day wonder, what would have happened if I'd done the abseiling and the particle accelerator thing? Where would I be now? Who knows? Anyway.